All right, so I'm back for another quick, and very sorry. In my mind, they're always going to be quick. Let's just go ahead and get that out of the way. Quick video though on the ideas of position and place value in decimal versus binary. And so I really want to talk just a lot about decimal uh, and the idea that it's a base 10 system, and then go back through and compare to binary. You know and love decimal so well that you do so much of this on autopilot. Like, you don't actively think about um, this a lot of the time. So these number symbols that we use and a place value system to use them with starts in India a long time ago, and it eventually spreads to the Middle East, and then it starts to spread from the Middle East into Europe around 800 years ago. So that's a very brief history lesson. These number symbols came from India to the Middle East to Europe. And so these are often referred to as the Hindu Arabic numerals to highlight that they started in India, traveled to the Middle East, and then finally to Europe. Let's just think about place value. A number like 5,187, you no longer have to actively think about, but if you were a kid, your teacher might work with you on expanded form. And the idea would be that it's 5,187. And you may not have ever even made it as far as, well, then it's 5 1,000s, 1 100, 8 10s, and 7 ones. And you probably definitely never looked at this with actually using exponents. It's a base 10 system because the base of the powers is 10. That's probably because humans have 10 fingers, is why this caught on. That bit of why they chose that is lost to time. Not every human society always used base 10 systems originally. For example, the Mayan civilization in Central America used a base 20 system. The ancient Babylonians used a base 60 system, which you would probably immediately think, well, that sounds awfully complicated. But hint, you still use some of the Babylonian base 60 system. That's why there's 60 seconds in a minute and 60 minutes in an hour. The Babylonians give us our calendars, which are about 360 days, 660s, and our timekeeping. And we've never really improved upon that system. We just use it. So this would be 5 times 1,000 is 10 to the third, plus 1 times 100 is 10 squared, plus 8 times 10 to the first, plus 7 times 10 to the 0. And so that's a fully expanded form using exponents. So we're making the powers of 10 kind of obvious. So because it's a base 10 system, you care about powers of 10, and you need 10 symbols, which means you would have a placeholder 0 and 9 symbols that represent digits. In this case, our place value was 4 digits. And you could even go as far as maybe even thinking about this a little more. but I think that's pretty good. So let's think about how it works in binary. Binary is a base 2 system, so we only need two numbers, two numerals. Our numerals that caught on and are fairly standard are 0 and 1. And you really need to start internalizing a central metaphor that binary is kind of like working with tiny little switches and you're flipping them on and off. And that's surprisingly accurate description of why computers use binary, because computers don't know anything about zeros and ones actually, but they sure can tell if there's electrical current flowing through a wire. And if the current's on, that's like a 1. And if the current's off, that's like a 0. So it's little teeny tiny light switches that can be rapidly switched on and off. That is also, fun fact that usually gets a few people, why most electronic devices have a power symbol that's a combination of a 0 and a 1. It's become a pretty standard symbol for power because 1 is the power is on, 0 is the power is off. So let's label the switch with the combination of a 0 and a 1. So in decimal, we still worked from right to left, and place value went up by powers of 10 because there were 10 number symbols. You also didn't need a second digit until you get to the 10th. If you count 0, these are all single digit numbers, and then you just sing a second digit at 10. You've rolled over. Think about, again, another central metaphor that helps kids understand binary is think about an old school car odometer that was actually based on like gears turning as the wheels of the car spun. If the odometer only kept track of miles with 5 digits and you had a car that you had driven quite a bit, it would roll over. So this phrase still gets used some. It would roll over the odometer back to 0 if you drove a mile. And of course, the car didn't really have 0 miles on it. It's just that the odometer didn't show very many digits. So, a modern odometer at 1 is computerized and 2 would have more digits. But that's the idea of cars rolling over on the odometer. And so these numbers roll over and need a second digit at 10. Binary, because there's only 2 symbols, it's going to roll over pretty fast. And so you end up needing, at least at first it seems like, you need a lot more place value. You should be able to quickly do this. Would like it better if those were a little more grouped. You should be able to quickly do this into groups of 4, and you generally tend to focus on 2 groups of 4 because that's a byte. That's the word that stuck. A byte was a group of 8 bits. Bit comes from binary digit. It starts with BI, it ends in IT, and so you called this one single place value where you're going to put either a 0 or a 1, a bit. It's a binary digit. The original Nintendo was an 8-bit system. So old school Mario, no improvements to the graphics or audio, was an 8-bit system. I can remember when that was cutting edge technology when I was around 10 years old. By the time I was in college, you were no longer talking about how many bits the system was because it had improved so much. It was a very large number. It was thousands of bits. A modern system, you all don't even, except unless you're in this class, really talk about individual bits. You talk about kilobytes or megabytes, or a new PlayStation might have even a terabyte hard drive. Your iPhone that fits in your pocket is more powerful and can handle more information and store more information than, a desktop computer could when I was your age. So we only have two symbols, and it might just be some ones and zeros, but this place value here is still worth 1. This place value here is worth 2, 4, 8, 16, 32, 64, 128. And if you kept going, it would just keep doubling because it's powers of 2. For instance, 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth, and so on. So it still is the same idea. It's just that you're really good at thinking in terms of thousands, hundreds, tens, and ones. You're not so good at thinking in terms of 8s, 4s, 2s, and 1s. So I hope that's a pretty good recap of position and place value in decimal versus binary. We'll do one quick example here. We'll fill in some numbers. We'll just do a 4-bit number, 1, 0, 1, 1. You would flip on the switch and turn on the 8. You would not flip on the switch and turn on the 4. You would flip the switch and turn on the 2. You would flip the switch and turn on the 1, and that would add up to 8, 2, 1 adds up to 11. If you want to be super abundantly clear, and you'll sometimes see this in print, is you want to maybe write the number in such a way that it indicates the base. And so it would not be uncommon to see, one last thing for this video, that 1011, you could write in binary, but that gets old fast. So what's pretty common, and I like to put a circle around it when I do it, but you won't actually see that in print very much, is you write a little subscript 2 to make it clear that it's a base 2 or binary number, is equal to, and some people will even use triple for equivalent, but that's probably not as common. But if you ever see a triple equal sign, that's somebody that's trying to be very careful and say, I get that really these things are not equal and the exact same thing. I'm trying to say that they have the same idea. Like, really, you shouldn't say that 4 quarters equals $1. You should say that 4 quarters, the little round metal disc, are equivalent to one rectangular piece of paper cloth with, $1 written on it. It's about symbols and that kind of thing, which gets us back into where all this comes from. I mean, it's all about symbols and information. But 1011 in base 2 is equivalent to 11 in base 10. Or if you want to be a little less careful, you could leave it to the reader to know that if you don't include a base, that you're talking about decimal or base 10 because that's the normal base. All right, I think that's it for now. Thanks for your time.